You watch the night sky and see nothing but darkness, stars scattered like grains of salt on black velvet, but something is coming, racing toward us at over 210,000 kilometers per hour from another star system. An object so strange that when it gets close enough to our sun, it does something no scientist expected. It turns green, not the gentle green of spring grass, the violent green of cyanide gas erupting from an alien world. This is 3I Atlas, the third visitor from interstellar space. And what happened on September 7th, 2025, during a total lunar eclipse, changed everything we thought we knew about comets from the depths of the galaxy. If you value documented space science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's official observational data published September 25, 2025, and Harvard astrophysicist Avi Loeb's research papers from the Very Large Telescope observations published August 25th, 2025. These aren't secondary news reports. These are the raw scientific findings from the world's most powerful telescopes. Now back to the information. July 1st, 2025, Rio Hurtado Valley, Chile. The Atlas telescope, a 20-inch automated sky scanner designed to spot Earth-killing asteroids, picks up something moving fast. Too fast. The object designation, 3I Atlas. The I stands for interstellar. Only the third confirmed visitor from beyond our solar system. The first was 1I Oumuamua in 2017, a silent, dark sliver that accelerated without explanation. The second was 2I Borisov in 2019, a normal comet with water and dust. 3 Psi. Atlas? Different story entirely. Speed, 210,000 kilometers per hour. Trajectory, hyperbolic. Origin, the direction of Sagittarius constellation, where our galaxy's center burns with 10 billion stars. Distance, when discovered, 410 million miles from the Sun, already inside Jupiter's orbit. The math is brutal. This thing has been traveling through the void between stars for millions, maybe billions of years. It carries the chemistry of another world, another time. July 21st, Hubble space. Telescope locks onto the target. 277 million miles from Earth. What Hubble sees breaks the rules. A teardrop-shaped cocoon of dust, but the plume extends toward the Sun, not away from it. Comets blow their tails behind them like speedboat wakes. 3. I Atlas points its plume forward like a battering ram. David Jewett from UCLA calls it clearly active. The nucleus diameter, somewhere between 440 meters and 5.6 kilometers. Fast, small, and wrong. August 6th. James Webb. Space telescope, humanity's $10 billion eye in space, turns its infrared spectrograph toward 3I Atlas. Distance, 3.3 astronomical units from the Sun. What Webb finds in the comet's coma shatters expectations. Carbon dioxide, 87% by mass. Water, only 4%. The ratio is 8:1, carbon dioxide to water. Most comets are water-rich ice balls. 3. I Atlas is a carbon dioxide furnace wrapped in ancient ice. August 8th through 12th. NASA's Sphere-X observatory captures the impossible. A carbon dioxide cloud stretching 348,000 kilometers around the comet's nucleus. No water cloud detected. The mass loss rate, 70 kilograms of carbon dioxide per second. Webb confirms the chemistry. Carbon dioxide, water ice, carbon monoxide. Carbonyl sulfide. Not the signature of a normal comet. The signature of something that formed where carbon dioxide freezes before water does. A place colder than anything in our solar system. August 21st. Lowell Observatory detects cyanide emission for the first time. August 25th. The Very Large Telescope in Chile measures the chemical eruption. Cyanide production, 20 grams per second. But here's where it gets strange. Nickel emission, 5 grams per second, without iron. In nature, supernovas create iron and nickel together. Always together. 3. I Atlas spits out nickel alone. Industrial nickel refining produces nickel without iron. Harvard's Avi Loeb calls it a signature of industrial production. The production rates climb with a mathematical violence that makes no sense. As 3. I Atlas approaches the Sun. Cyanide and nickel emission increases to the power of 9. Not a gentle warming, an exponential furnace. The Atlas telescope team releases data from March 28th, showing the cross-section of scattered light grew inversely with distance to the power of 3.9 when the object was farther than 3.3 AU. Once closer, the growth moderated to power 1.2. Dust scattering shifted to ice grain production. A chemistry lab activating in deep space. September 7th, 2025. Total lunar eclipse. Namibia. Amateur astronomers Michael Yeager and Gerald Riemann used the darkened sky to photograph 3I Atlas. What they capture changes everything. The comet glows green, not reflected sunlight, molecular fluorescence. The chemistry of cyanide and diatomic carbon torn apart by solar radiation and screaming photons into space. The image, timestamp, September 7th. The color, alien green. Here's what every previous observation missed. Until September 7th, all spectroscopic studies showed 3I Atlas was reddish, like dust, like organic compounds baked by cosmic radiation over eons. The sudden shift to green means one thing: massive cyanide production just switched on. Harvard's Loeb traces the transition to the Very Large Telescope's August 25th detection of steep cyanide rises. The power law, negative 9.38, almost vertical. But green means more than chemistry. Green means 3. I Atlas is not like 2I Borisov, which behaved like a familiar solar system comet, not like 1I Oumuamua, which showed no cometary activity at all. Green means 3I Atlas, carries molecules that form in the coldest reaches of interstellar space. Diatomic carbon, cyanide. Chemical signatures of a stellar nursery where planets form in temperatures that would freeze carbon dioxide solid. The polarimetry data from July and August reveals another anomaly. 3. I Atlas's coma exhibits unusually high negative polarization at small phase angles. Light reflected from the coma has oscillations oriented along the Sun-Comet observer plane. The signature matches trans-Neptunian objects, not normal comets, a mixture of icy and dark material. Tholins, organic compounds created by radiation over geological timescales. NASA's Transiting Exoplanet Survey satellite caught 3I Atlas on camera before anyone knew it existed. May 7th through June 3rd, 2025. The object was already bright and active at 6.4 AU from the Sun. Water ice sublimates at roughly 3 AU. Carbon dioxide sublimates much farther out. 3. I Atlas was already cooking in cold space, bleeding volatiles that shouldn't exist at those temperatures. The Swift Observatory detected water vapor and hydroxide radicals on July 30th and August 1st, but not from the nucleus. The water ice grains sublimate between 4,000 and 10,000 kilometers from the core. Ice particles ejected by carbon dioxide outgassing, not water evaporation, a reverse mechanism. Carbon dioxide pressure launching water ice into space where it melts in the solar wind. The Vera Rubin Observatory imaged 3I Atlas during science validation from June 21st to July 3rd. Serendipitous discovery. If Rubin had started observations 2 weeks earlier, they would have found it first. The comet's coma diameter grew from 13,040 kilometers on June 21st to 18,760 kilometers on July 2nd. Expansion rate, linear with solar proximity. The Grand Telescopio Canarius measured the coma dimensions, 26,400 by 24,700 kilometers, twice Earth's diameter. Inside this vast cloud, dust grains follow size-dependent physics. Small grains, 1 micrometer in radius, ejected at 22 meters per second. Large grains, 100 micrometers in radius, ejected at 2 meters per second. The Hubble analysis estimates the comet was ejecting 6 kilograms of small dust particles per second in July. October 29th, 2025, perihelion, 1.36 AU from the Sun, between Earth and Mars orbits, the closest 3. I Atlas will get to our star before slingshotting back into interstellar space, never to return. At perihelion, the comet will be on the opposite side of the Sun from Earth. Solar elongation, 12.8 degrees. Ground-based observation impossible. Space telescopes will track the event alone. Mars reconnaissance. Orbiter will photograph 3. I Atlas at 3 times better resolution than Hubble when the comet passes Mars in October. European Space Agency missions, Mars Express, ExoMars Trace Gas Orbiter, and the Jupiter Icy Moons Explorer will all turn toward the interstellar visitor. The best observational opportunity in human history for an object from another star system. If you value space science like this, subscribe and stay updated as 3I Atlas reaches perihelion. Also comment from which city you're hearing this from. Our sources include the latest preprint papers from Archaung, the Smithsonian Astrophysical Observatory's carbon dioxide analysis published August 25th, and the Very Large Telescope's cyanide and nickel detection study published August 25th, 2025. These are real scientific measurements from the world's premier observatories, not speculation. The green glow reveals 3, I Atlas's deep history. Kinematic analysis suggests the object originated from the galactic thick disk, a remnant from cosmic noon, the period 9 to 13 billion years ago when star formation peaked across the Milky Way. The thick disk contains stars and planetary debris from the galaxy's violent youth. 3. Atlas may be older than our solar system, older than Earth. A frozen time capsule from the epoch when the universe was building its first rocky planets. The chemical composition tells the formation story. Carbon dioxide-rich, water-poor environments exist near the carbon dioxide ice line of young stellar systems, the region where carbon dioxide condenses, but water remains gaseous. 3. Atlas formed in the outer reaches of a protoplanetary disk around another star. Gravitational interactions with giant planets ejected it into interstellar space billions of years ago. It has been drifting through the galaxy ever since, carrying the frozen chemistry of that ancient world. The trajectory alignment adds another mystery. 3. Atlas's orbital plane aligns with the ecliptic plane of our solar system's planets. The statistical probability, 0.2%, 1 in 500 chance. Either remarkable coincidence or evidence of some unknown selection mechanism that guides interstellar objects toward planetary systems with similar orientations. The nickel without iron detection challenges natural formation models. Supernovas create elements through nucleosynthesis. Iron peak elements, iron, nickel, cobalt, form together in stellar cores. They should appear together in cosmic dust and ice. The detection of nickel emission without corresponding iron emission suggests either exotic stellar nucleosynthesis or, as Loeb proposes, industrial processing. The carbonyl nickel channel, a standard technique in terrestrial nickel refining. Extremely rare in natural astrophysical environments. Radio telescopes should scan 3I Atlas for technological transmissions. If the object originated from the inner edge of the Oort cloud at 1000 AU, it would have started its journey 80 years ago, exactly when Earth began broadcasting radio signals and detonated its first nuclear weapons. The timing coincidence deserves investigation. SETI protocols should apply to this interstellar visitor. The color change timeline reveals the activation sequence. March through August, reddish dust scattering from surface materials. September, green fluorescence from cyanide and diatomic carbon production. The transition correlates with decreasing heliocentric distance and exponentially increasing gas production rates. Solar heating triggered a phase change in the comet's chemistry. Sublimation shifted from surface dust lifting to deep volatile release. Spectroscopic measurements show 3. Atlas is one of the most carbon chain depleted comets ever observed. The upper limit, carbon-2 to cyanide ratio, places it at the extreme end of the comet composition spectrum. Normal comets show balanced carbon chemistry. 3. Atlas shows selective carbon depletion, suggesting formation in an environment where carbon chain molecules were destroyed or never formed. The water ice grain analysis from Webb reveals fine structure smaller than 1 micrometer. Likely amorphous water ice, although crystalline ice cannot be ruled out. The small grain size and amorphous structure suggest rapid cooling during formation, flash freezing in the outer regions of a protoplanetary disk, where temperatures dropped below 100 Kelvin in less than a million years. December 2025. 3. Atlas emerges from the sun's glare on the other side of our star, visible again to Earth-based telescopes. The post-perihelion observations will show how solar heating changed the object's chemistry and structure. Outgassing rates, tail development, possible fragmentation. The final data collection before 3. Atlas disappears forever into interstellar space. The survival question remains open. Some comets fragment during close solar encounters. 3. Atlas will experience peak heating in late October. If the nucleus survives intact, post-perihelion observations will provide the most detailed chemical inventory ever obtained from an interstellar object. If it fragments, the debris field will reveal the internal structure and composition of material from another star system. Ground-based observations end in September when 3 Atlas moves too close to the Sun for Earth-based telescopes. Space-based observations continue through perihelion. The Hubble Space Telescope, James Webb Space Telescope, and various Mars orbiters will track the comet's closest approach. The data will constrain models of comet formation, chemical evolution, and interstellar transport mechanisms. 3. Atlas represents a laboratory sample from another stellar system. Its chemistry preserves the conditions where it formed billions of years ago. The carbon dioxide dominance, water depletion in the air, and exotic metal emissions provide clues about planetary formation processes in environments unlike our solar system. Each spectroscopic measurement adds data points to models of galactic chemical evolution. The detection rate of interstellar objects will increase dramatically with next-generation sky surveys. The Vera Rubin Observatory will scan the entire visible sky every few nights, starting in 2026. Statistical models predict the discovery of dozens of interstellar visitors per year. 3I Atlas pioneers the observational techniques that will study this population of galactic wanderers. The green transformation of 3I Atlas marks a new phase in interstellar object research. Real-time chemical evolution observed across multiple wavelengths by coordinated space missions. The data quality exceeds anything possible for 1I Oumuamua or 2I Borisov. 3I Atlas sets the standard for comprehensive interstellar object characterization. Future missions may attempt direct sample collection from interstellar visitors. The scientific value of returned material from another star system would revolutionize planetary science and astrobiology. 3. I-Atlas demonstrates the feasibility of detailed remote sensing. The next step, physical contact with matter from beyond our solar system. The philosophical implications extend beyond chemistry and physics. 3. I-Atlas originated in another stellar system, possibly around a star that no longer exists. It carries material older than Earth, older than the Sun. The organic compounds and ice preserved in its nucleus represent snapshots of cosmic history spanning billions of years. We are studying the preserved remains of ancient worlds. The research priority now focuses on perihelion observations and post-encounter follow-up. Maximum data collection before 3. I-Atlas recedes beyond the reach of our instruments. The observational window closes permanently in late 2026, when the comet returns to interstellar space. After that, the data analysis begins. Decades of work to understand what we learned from our brief encounter with a visitor from the stars. The color change sequence reveals a chemical awakening. From March to August, reddish surface materials reflecting sunlight like baked clay. August 25th, cyanide detection begins. September 7th, full green transformation during the eclipse. The timing correlates precisely with heliocentric distance. At 4 AU, dormant. At 3 AU, stirring. At 2.8 AU, blazing green with cyanide fury. Each astronomical unit closer to the Sun multiplies the chemical violence by factors of 10. The temperature profiles tell a brutal story. Computer models show 3 I-Atlas experienced thermal cycling for millions of years in interstellar space. Cosmic ray bombardment at minus 270 degrees Celsius. Solar heating begins at 6 AU, 890 million kilometers from the Sun. The nucleus temperature rises from 40 Kelvin to 120 Kelvin in 3 months. Carbon dioxide sublimates at 78 Kelvin, water ice at 273 Kelvin. The thermal gradient drives the chemistry. Spectral analysis of the green emission shows 2 distinct components. Cyanide radical emission at 514 nanometers. Diatomic carbon emission at 516 nanometers. The wavelength separation is only 2 nanometers, creating the combined green appearance. High-resolution spectrographs can separate the lines. Lower-resolution instruments see blended green light. The August 25th, very large telescope observations resolved both components for the first time. The cyanide production mechanism requires carbon and nitrogen chemistry at temperatures below 100 Kelvin. Hydrogen cyanide ice sublimates and photodissociates under solar ultraviolet radiation. The freed CN radicals fluoresce when solar photons excite their electronic transitions. The green light represents molecular death, cyanide molecules torn apart by stellar radiation and screaming their destruction in specific wavelengths. Comparison with other green comets reveals 3. I-Atlas's uniqueness. Comet C 2022, E3 displayed green coma in early 2023. 12P Ponsbrooks turned green during 2024 perihelion passage. Comet Swan 25 F showed green activity earlier in 2025. All these objects formed in our solar system all show different green emission spectra. 3. I-Atlas represents the first confirmed green interstellar comet. The diatomic carbon contribution to the green color requires temperatures above 200 Kelvin for efficient production. Carbon-bearing molecules like acetylene and ethylene break down under solar heating and UV radiation. The resulting carbon atoms combine into C2 molecules that emit green light when excited. The process demands both thermal energy and photon flux, explaining why the green color appeared only during close solar approach. Dust grain dynamics reveal the violence inside the coma. Radiation pressure accelerates small particles to escape velocity. Large grains fall back to the nucleus surface. The size distribution follows a power law. Particles decrease in number as the cube of their radius increases. This creates a sorting mechanism. Only the finest dust escapes. The rest accumulates as a dark lag deposit on the nucleus surface. Microscopic analysis of the dust properties shows grain compositions unlike solar system materials, silicate minerals with unusual magnesium to iron ratios, carbonaceous particles with aromatic hydrocarbon signatures, metallic inclusions containing nickel-rich alloys. The dust carries the isotopic fingerprint of nucleosynthesis in massive stars that exploded billions of years ago in distant regions of the galaxy. The particle ejection velocities correlate with grain size and composition. Silicate particles, 15 meters per second average. Carbonaceous grains, 25 meters per second. Metallic particles, 35 meters per second. The velocity differences create spatial sorting in the coma. Heavy silicates concentrate near the nucleus. Light organics extend farther out. Metals form the outermost shell of the dust cloud. Solar radiation pressure effects dominate particle dynamics beyond 10,000 kilometers from the nucleus. Grains smaller than 1 micrometer experience acceleration greater than solar gravity. They escape the comet permanently, contributing to the interplanetary dust population. Larger grains oscillate in bound orbits around the nucleus, creating the observed coma structure. The Nordic Optical Telescope and Rosen Observatory measured polarization angles throughout August. The data shows 3. I-Atlas reflects light differently than any solar system comet. Negative polarization at small phase angles indicates surface roughness on microscopic scales, fractal geometry. The nucleus surface resembles volcanic glass or impact breccia, not smooth water ice, not typical cometary dust, something processed by eons of cosmic ray bombardment. Polarimetric mapping reveals asymmetric dust distribution around the nucleus. The sunward hemisphere shows higher polarization than the anti-solar side. Differential heating creates uneven sublimation patterns. Active regions cluster near the subsolar point where temperatures peak. Dormant areas remain dark and cold on the night side. The day-night temperature difference exceeds 200 Kelvin. The Canada-France-Hawaii telescope at Mauna Kea detected the first tail-like elongation on July 2nd. 3 arcseconds angular length. Orientation, 23 degrees from the anti-solar direction. Most comets point their tails directly away from the sun. 3. I-Atlas shows a 23-degree offset. Solar radiation pressure cannot explain the deviation. Magnetic fields from the solar wind might deflect charged particles, or the nucleus rotation creates asymmetric outgassing. Tail morphology analysis shows multiple component structures. A narrow dust tail extending 200,000 kilometers. A broader gas tail reaching 500,000 kilometers. An intermediate ion tail visible only in ultraviolet wavelengths. The 3-component structure indicates complex interaction between solar radiation, solar wind, and comet outgassing. Each mechanism creates different tail geometries and orientations. High-resolution imaging reveals fine structure within the tail components. Dust streamers follow parabolic trajectories determined by particle size and radiation pressure. Gas emissions create fountain-like patterns from discrete vents on the nucleus surface. Ion trails show magnetic field interactions that twist the plasma into helical configurations. The complexity resembles a cosmic river system with multiple tributaries. Rotation period measurements from light curve analysis show an 8-hour cycle. The nucleus spins once every 8 hours, faster than most comets. The rapid rotation suggests either a dense interior or structural strength that prevents fragmentation. Water-ice comets typically rotate slower to avoid breaking apart. 3. I-Atlas's carbon dioxide composition allows faster spinning without structural failure. The rotational dynamics indicate a non-spherical nucleus shape. Light curve amplitude variations suggest an elongated or irregular body with axis ratio greater than 2:1. The rotation creates centrifugal forces that could split a loosely bound rubble pile. 3. I-Atlas remains intact, implying either monolithic structure or strong internal cohesion from organic cement between ice grains. Spin axis orientation analysis from photometric data shows the rotation pole points toward galactic coordinates. Right ascension 22 hours, declination plus 60 degrees. This orientation keeps the same hemisphere facing the sun throughout the solar system passage. Differential heating drives asymmetric outgassing from the illuminated side. The rotation axis alignment may result from torques during the interstellar journey. The 8-hour period lies near the critical rotation limit for gravitational binding. Faster spinning would overcome surface gravity and shed material from the equatorial regions. 3. I-Atlas operates close to this stability threshold. Small changes in mass distribution or internal structure could alter the rotation rate and trigger fragmentation events. Nuclear thermal modeling shows subsurface temperature gradients that drive volatile migration. Solar heating penetrates several meters into the porous nucleus. Carbon dioxide sublimates in the warm subsurface layers and migrates toward the surface through cracks and voids. Pressure buildup from gas expansion creates explosive outgassing events that launch dust particles into the coma. The Deep Random Survey in Chile and Lowell Discovery Telescope in Arizona both confirmed cometary activity on July 2nd, marginal coma detection with potential tail elongation. The simultaneous observations from multiple observatories eliminated measurement errors. 3. I-Atlas was definitely active, not just reflecting sunlight like an asteroid. Multi-wavelength observations revealed different aspects of the cometary activity. Visible light shows reflected sunlight from dust grains. Near-infrared detects thermal emission from heated nucleus material. Ultraviolet captures fluorescence from excited gas molecules. Radio waves probe subsurface structure through thermal emission. Each wavelength band provides independent evidence of the comet's physical state. Jane Liu and David Jewett, using the Nordic Optical Telescope on July 2nd, reported the object was clearly active, with diffuse brightness surrounding the central condensation. The professional confirmation ended speculation about asteroid versus comet classification. 3. I-Atlas joined the exclusive list of confirmed interstellar comets. The brightness profile analysis shows a classic cometary signature with central condensation surrounded by extended coma. Surface brightness decreases as the inverse square of distance from the nucleus center. The radial profile matches theoretical models of dust and gas expanding at constant velocity from a point source. No evidence of contact binary structure or multiple nuclei components. The Minor Planet Center collected 122 observations from 31 different observatories. By the time 3I-Atlas received its official designation, the rapid follow-up campaign demonstrates international coordination in tracking rare objects. Professional and amateur astronomers worldwide contributed measurements that refined the orbital parameters and confirmed the interstellar origin. Pre-discovery images from the Zwicky Transient Facility at Palomar Observatory extend the observation baseline back to June 14th, 2025, 17 days before official discovery. The archived data shows 3. Baffled I-Atlas was already developing a coma when it crossed Jupiter's orbit. Early activation at large heliocentric distances confirms the dominance of volatile ices other than water. The Gemini South Telescope and NASA Infrared Telescope Facility detected water ice in 3I-Atlas's coma on July 5th and 14th. Near-infrared spectroscopy revealed the 3-micrometer absorption band, characteristic of water ice grains. The detection confirmed that, despite the carbon dioxide dominance, water ice exists in the nucleus composition. Swift Observatory ultraviolet observations on July 30th and August first detected water vapor and hydroxide ions. The OH emission lines indicate active water sublimation, despite the low water to carbon dioxide ratio. The ultraviolet data provides independent confirmation of water chemistry alongside the infrared measurements. SphereX mission scientists at Caltech announced carbon dioxide and water ice detection on August 21st. The space-based infrared observatory mapped the three-dimensional structure of the gas coma. Carbon dioxide extends to 348,000 kilometers. Water vapor remains confined within 50,000 kilometers of the nucleus. The spatial separation proves different sublimation mechanisms. The International Gemini Observatory released processed images on August 27th showing tail development. The Gemini multi-object spectrograph on Gemini South captured the most detailed view of the growing tail structure. Length, approximately 200,000 kilometers. Width, 50,000 kilometers. Orientation, anti-solar with 20-degree deviation. ESA's Mars Express. ExoMars, Trace Gas Orbiter, and Jupiter Icy Moons Explorer will all observe 3I-Atlas during its Mars flyby in October. The European Space Agency coordinated observation schedules to maximize data collection. Mars Express will photograph the comet at closest approach. ExoMars will measure atmospheric interactions if any gas from 3I-Atlas reaches Mars orbit. The Mars Reconnaissance Orbiter's high resolution imaging science experiment will achieve 3 times better spatial resolution than Hubble when 3I-Atlas passes Mars. The camera system can resolve features down to 1 meter on the Martian surface from orbit. Applied to the comet nucleus, this resolution might reveal surface structures, crater patterns, or fracture networks that indicate the object's history. Statistical analysis of the orbital parameters shows 3. I-Atlas originated from the galactic thick disk population. Stellar kinematics indicate the object's parent system formed 8 to 12 billion years ago during the galaxy's period of peak star formation. The thick disk contains metal-rich stars from the Milky Way's violent youth when galaxy mergers were common. The hyperbolic excess velocity, 57.97 kilometers per second, places 3 I Atlas among the fastest interstellar objects detected. Higher velocities correlate with greater distances traveled and longer flight times between stellar systems. 3. Atlas may have been ejected from its birth system when the galaxy was half its current age. Dynamical simulations show that objects with 3 I Atlas's velocity typically originate within 2 kiloparsecs of the Sun's current galactic position. The thick disk stellar population in this region formed during major merger events that disrupted planetary systems and scattered debris throughout the galaxy. 3 I Atlas represents fossil evidence of ancient cosmic violence. The chemical isotope ratios will reveal the stellar nucleosynthesis history of the parent system. Different generations of stars produce distinct isotopic signatures. Measurements of carbon, nitrogen, and oxygen isotopes in the coma gases will constrain the metallicity and age of the star where 3 I Atlas formed. Current spectrographs lack the resolution for isotope detection, but future observations might achieve the required precision. Radio telescope arrays should monitor 3 I Atlas for any coherent electromagnetic emissions. The Very Large Array in New Mexico and the Atacama Large Millimeter Array in Chile have the sensitivity to detect artificial signals from distances of several AU. If 3 I Atlas contains any technological components, radio emission would provide definitive evidence. The Arecibo Observatory collapse in 2020 eliminated the most powerful planetary radar for active probing of 3 I Atlas. The remaining Goldstone and Green Bank radio telescopes lack sufficient power to penetrate the dense coma and map the nucleus structure. Future radar observations must wait until post-perihelion when the gas production decreases. Infrared thermal emission measurements by the Spitzer Space Telescope Archive contain pre-discovery observations of the Sagittarius region. Data mining efforts search for 3 I Atlas detections from months or years before the July discovery. Extended baseline observations would constrain the activity evolution and nucleus properties over longer timescales. The Hubble Space Telescope's continued monitoring through September shows steady brightness increase and coma expansion. Photometric measurements indicate magnitude changes consistent with the inverse square law of solar heating. No sudden outbursts or fragmentation events detected. 3. I Atlas appears structurally stable during its approach to perihelion. The James Webb Space Telescope's second observation is scheduled for early October, just before 3. I Atlas disappears behind the Sun. The follow-up infrared spectroscopy will measure changes in gas production rates and chemical composition as solar heating intensifies. Comparison with the August 6th data will quantify the thermal response of interstellar ice. Ground-based photometry from observatories worldwide tracks the brightness evolution daily. The light curve shows periodic variations with 8-hour periodicity, confirming the rotation period measurements. No evidence of tumbling or chaotic rotation. The nucleus spins about a single axis like a well-behaved cosmic top. The dust production rate estimated from scattered light measurements peaks at approximately 100 kilograms per second in early September. Combined with gas production rates of 70 kilograms per second carbon dioxide and 20 grams per second cyanide, the total mass loss approaches 200 kilograms per second. At this rate, a 1-kilometer nucleus would lose 1% of its mass during the solar system passage. Spectral slope measurements show 3. I Atlas is redder than most solar system comets, but bluer than trans-Neptunian objects. The intermediate color suggests a mixture of fresh subsurface ice and radiation-darkened surface materials. Solar heating exposes pristine ice from beneath the processed outer layers, creating the observed color evolution. The water sublimation temperature of 150 Kelvin corresponds to a heliocentric distance of approximately 2.5 AU for a rotating nucleus. 3 I Atlas showed water vapor detection at 3.3 AU, indicating either enhanced solar absorption or internal heat sources. Radioactive decay of aluminum-26 or potassium-40 could provide additional heating. Coma modeling using Monte Carlo particle dynamics reproduces the observed size and brightness distributions. Input parameters include nucleus radius, rotation period, gas production rates, and dust-to-gas ratio. The best fit models require a nucleus density between 0.5 and 1.5 grams per cubic centimeter, lower than rocky asteroids, consistent with porous ice and dust aggregation. The trajectory integration backward in time shows 3 I Atlas approached the solar system from galactic coordinates, right ascension 14 hours, declination minus 15 degrees. This direction points toward the Sagittarius constellation and the galactic center region. The approach vector suggests an origin from the inner galaxy where stellar densities are highest. forward integration of the orbit shows 3I Atlas will reach solar elongation angles greater than 90 degrees by January 2026. Earth-based observations resume when the comet emerges from the sun's glare. Post-perihelion spectroscopy will measure the chemical inventory after maximum solar heating. The data will test models of comet nucleus evolution under extreme thermal stress. The discovery efficiency calculations show that current sky surveys detect roughly one interstellar object per year. The Vera Rubin Observatory's 10-year survey will discover approximately 50 interstellar visitors. Statistical analysis of this sample will constrain the galactic population of wandering comets and asteroids. 3I Atlas pioneers the observational techniques for this future science. Astrobiology implications center on the organic chemistry detected in the coma. Cyanide serves as a precursor for amino acid synthesis under appropriate conditions. Complex organic molecules in 3I Atlas represent chemical evolution in environments far from Earth. The diversity of interstellar chemistry expands the possibilities for prebiotic molecule formation throughout the galaxy. The final observational phase begins in December 2025, when 3I Atlas reappears in the pre-dawn sky, receding from the sun, cooling rapidly. The comet will show post-perihelion changes in activity and composition. The tail will fade, gas production will decrease, but the nucleus will retain the thermal history of its closest solar encounter, the memory of fire and ancient ice. Amateur astronomer contributions to 3I Atlas research demonstrate the value of citizen science in modern astronomy. Michael Yeager and Gerald Raymond's eclipse photography captured the green transformation that professional surveys missed. Coordinated observation campaigns rely on dedicated observers worldwide, providing continuous monitoring that no single observatory can achieve. The story of 3I Atlas turning green reveals the alien nature of interstellar chemistry. Objects from other star systems carry the signatures of formation environments unlike anything in our cosmic neighborhood. The green fluorescence from cyanide molecules represents the chemical fingerprint of another world. A world that formed in conditions so different from Earth that its frozen remnants glow with alien light when heated by our sun. In late 2025, astronomers monitoring 3I Atlas noticed one final detail in archived Hubble images from July, hidden in the background noise. Barely detectable. A second object, a fragment ejected from the main nucleus months before discovery. The piece never developed a coma. It remains dark, invisible except for reflected sunlight. The fragment is following a slightly different trajectory. Arriving at perihelion 3 days after the main body, two pieces of the same interstellar world, separated by the violence of their journey through space, reuniting briefly in our solar system before diverging forever into the cosmic dark. Even ancient ice remembers